Okay, so today we are going to learn how to balance redox reactions. So we've talked about what reduction is, we talked about what oxidation is, we've learned how to find oxidation numbers, and we already know how to balance equations, right? So we're going to throw all of that into one bucket. Okay, so first of all, there are two different types. We can balance redox reactions in an acidic condition, and we can balance redox reactions in a basic solution. You basically do the same thing, but except acids have hydrogen, whereas bases have hydroxide. So it's just one additional step. Okay, so to balance redox reactions in acidic conditions, first of all, our electrons have to be equal. We all know that elements will gain and lose electrons to make them stable, correct? So we have to make sure that we start with the same amount of electrons as we end up with, so that it's still conservation of mass. We can't lose electrons. Okay, we also have to learn how to create a half reaction. Okay, basically, in a reaction, two things are happening a lot of times in acidic and basic solutions. So we're going to break them up and look at them individually and then put them back together. So to do this in an acidic condition, basically what you do is you divide the equations into your half reactions. One for the oxidation step, so somebody is losing, right? Losing electrons, because oxidation means you lose electrons. So you break apart the oxidation step. Then you break apart the reduction step. Remember, reduction is gaining electrons. I use the mnemonic device oil rig to remember that. And not only, but I want you to kind of add something to the first step. So use your pencil. Add to the first step. I want you to add that in this step, you need to figure out your oxidation numbers. Okay, if you figure out your oxidation numbers right here, it's going to help you in the next couple of steps. Oh. Nice. Nothing. I already added it for you, apparently. I did. I was nice and I added it for you. I forgot I did that. Number two, after you have found out the oxidation numbers, I want you to then balance the half reactions. Because like I kind of just talked to you about manganese oxide, right? It forms a different type of manganese oxide. So you need to balance that. You can't have 4 oxygen on the left and only 2 on the right. So you need to balance it first. Okay, what you do, if you guys remember from chemistry, I tried to already teach you this habit. You do everything except for hydrogen and oxygen, right? I tried to teach you that habit in chemistry last year. Okay, so once you get everything balanced besides hydrogen and oxygen, in order to balance oxygen, you need to add water. So instead of changing the coefficient in front of your oxygen compound, once everything else is balanced, if oxygen still is unbalanced, you need to add water to whichever side needs it. Okay, then you balance your hydrogen by adding the hydrogen ion to whatever side you didn't add your water to. So, and I'm going to do an example in just a minute. But when you add water to one side to balance oxygens, that's obviously going to throw off your hydrogen, right? So then to balance out your hydrogen, you add hydrogen to the other side. Water on one side, hydrogen on the other. Okay. So there's step 2. After you do that, you are going to multiply each side to get your electrons to balance out. So we have to add electrons to our equation now because we have ions. We can't just lose electrons, right? So we also have to balance our electrons because our oxidation numbers are changing. Okay, but most likely you're not going to get equations that have the same number of electrons on each side. So we're actually adding an additional balancing step. We know how to balance equations, but we've probably never done them where we have to balance out electrons. So in order, you want the same number of electrons on each side so that they will cancel out, kind of like our net ionic equations. So in order to do this, we have to multiply each half equation by some number to get our electrons to cancel out. Okay, then after you've done all of that and you have gotten your electrons to cancel out, then you add the half reactions together, you cancel out all of your like terms, kind of like we did in the net ionic equations. Then, last but not least, until you get good at this, you need to double check your charges. You need to make sure that everything's balanced. You need to make sure that your oxidation numbers all match up. You haven't lost any electrons, so on and so forth. So until we get good at this, double check your work. So let's do an example. Okay, so in an acidic solution, which is what we are doing right now, we are going to take manganese oxide and we are going to add it to chromic acid. That's what C2O4 is. That's chromic acid. And we are going to get manganese, a manganese ion, and carbon dioxide, which if you look at your cheat sheet that I gave you for important oxidizers, we see that in an acid solution, manganese oxide will form the manganese ion, right? Correct? The other what? That one, it doesn't matter. It's always going to be an oxidizer. Okay, so first step, we need to, I'm going to break them into half reactions and I'm going to find oxidation numbers right off the bat, okay? So, and I'm just going to try to write all of this. So let's start with our first one, which is manganese, and I need a color that you can read. So we're going to start with Mn. You can't read that. Right. So I'm going to start with this reaction, and I'm going to figure out some oxidation numbers. We know the oxidation number of oxygen, okay? And I'm just going to go right out and tell you that this is not a peroxide, so we're going to treat this as oxygen is -2, okay? So our oxygen, this is -2. So in order to figure out manganese, we have to do a little bit of math, right? So manganese plus 4 oxygens has to equal -1, because this is a polyatomic ion with a charge of -1. So therefore, our manganese has to equal 7 positive. So this manganese has an oxidation number of 7 positive. This manganese over here has an oxidation number of 2 positive. Can we lose electrons? No. So now we have discovered the oxidation number, so it's going to help us in the next step determine what we need to do. Okay. Let's do the same thing for chromic acid or chromate. So we're going to have C2O4 2 minus, and that's going to form CO2, correct? Let's figure out the oxidation number of carbon because we know oxygen is -2. So 2 carbons plus 4 times -2 has to equal 2 minus. So 2C minus 8 equals -2. So then we get 2C equals 6, and then C has to equal 3. So this carbon has a charge of 3 positive. Now, we also have to do that to the other side, don't we? Okay, because it's not by itself, so we have to do it to the other side as well. So, oxygen, we don't know what carbon is. We know that oxygen is -2, and this time we have to set it equal to 0. So our carbon is going to be equal to 4 positive. Well, our charge changed, didn't it? So that means an electron is just kind of lost somewhere in here. So we have to balance our equations not only with elements, but now with electrons as well. Okay, so there was the first step. We have figured out our half reaction, well, the first couple steps. We've done our half reactions, we have figured out our oxidation number, so now we can start the whole balancing process. So now what I'm going to do is we have to balance the elements other than hydrogen and oxygen first, right? So let's look up at our manganese oxide, manganese. Well, everything but oxygen is already balanced, right? So now we can move on. We need to balance oxygen. How do you balance oxygen? You add water. How many waters do we need to add? 4. Why do I need to add 4 waters? We have 4 oxygen on the left, so we need 4 on the right. Each water only has 1, so I have to add 4 waters over here. To balance, but now I've added hydrogens, correct? Yes. So how do I fix that? Add hydrogen ions to the reactant side. I need hydrogen ions on the reactant side. How many hydrogen ions? 4. Or no, 8. 8. Why am I using H plus as opposed to my diatomic molecule H2? Because this is an acidic solution. So we know we have hydrogens floating around, correct? And it's not a solid, it's not an elemental form, it's in solution. This is all dissolved in water. So then, why do you have coefficients for water and hydrogen instead of Say what?
Instead of putting like subscripts like for water, putting a 4, saying you have 4 of those, why do you have coefficients instead? Because you put 4 H2O instead of H2O with a 4 subscript.
Because remember, subscripts make the compound neutral. This coefficients give you multiple. So if I put H2O4, that means it would be bonded to something with a positive. You use subscripts to make compounds neutral. You don't use subscripts to give you multiple ones. Does that make sense? I think, yes. So we need to do the same thing to our bottom one. We need to balance everything but hydrogen and oxygen first. So now we need to balance our carbons. How do I balance my carbons? I put a coefficient of 2 in front of carbon, so that fixes my carbon problem and my oxygen problem, right? So do I need to add oxygens and hydrogens? Nope, because I'm already balanced. Okay, so we've done A, we've done B, we've done C. Now we need to balance the charges. Yes, Kaylee?
When we added waters, isn't there 8 oxygens though? And
Why would there be 8?
oh wait, I was looking at the one right at the beginning. Sorry, I was looking at the top one.
Oh, okay, got it. All right, so now we have balanced everything. We balance everything but hydrogen and oxygen. We balance oxygen, we balance hydrogen. So now we need to balance the charge. Luckily for us, we already wrote our oxidation number, so we know what we need to balance. The hydrogens have the same charge on both sides. The oxygens have the same charges on both sides, so we don't have to worry about those. The only thing we need to be worrying about is manganese and carbon. So manganese started off as 7 plus. It ended as 2 plus. So what happened? Did it gain or did it lose electrons? It gained. It became less positive. So to become less positive, don't you gain electrons? Yes. So where am I going to put my electrons on this one? On your product side. Wait, no, on your reactant side. Basically, you want these two numbers to be the same. So to make, all we can do is add negatives, right? We can't add positives. So which side do we need to add negatives to make the positive 7 and the positive 2 the same? The left. How many do we need to add? And I'm running out of room. 5 electrons. We're going to do the same thing to carbon. We have to look at the charges. We have +3, we have +4. There was an electron change happening there. We can't lose any. So which side can we add electrons to make that the same number? We're going to add 1 electron on this side. Okay, so now we're done with the balancing of our half reactions. Everything is balanced. Our charges are balanced. Yes, Tanya? We didn't gain an electron. We lost an electron, but it didn't just disappear into space, so we have to put it in the equation. So if you were to put that back on carbon, then the oxidation number would have stayed the same. Okay?
So we only look at the electrons and minerals when we do electrons that aren't hydrogen or oxygen? Because you don't have to look at the
Not always, but most of the time, yeah. Oxygen and hydrogen are not going to be the ones that their oxidation numbers are changing because they're the ones that are the rules. So oxygen's very highly electronegativity. Its oxidation number is probably not going to change. Hydrogen's pretty high up there too, so probably not going to change. Manganese, low oxidation number, or low electronegativity. It's the one that's probably going to be forced to change. Carbon, again, low electronegativity. It's probably going to be the one that's forced to change. There's never an always in chemistry.
So then we have like if I'm not saying oxygen will have to change, but if there was a change, like if we see the charge then it would be different when we do with oxygen and
Uh-huh.
things like that.
Mhm.
So
Yes.
basically the numbers we have we just put the plus electrons into our size.
Mm-hmm. Mm-hmm. Yes.
Okay, so the reason why we put the electron on the right side
Uh-huh.
if we wanted to put a compound number.
Mm-hmm. No, it's just balancing. We have that many electrons on the left, but when we move from the left to the right of that second half, with that second half reaction, Our charge changed. Well, and the only way you can change a charge is if you lose an electron or gain an electron, right? But it doesn't just, in this one, it says we lost an electron. We can't lose an electron, conservation of mass. It didn't just disappear. So we're just putting it in the equation so that it didn't just disappear. Okay? All right, so let's see if we can move on to the next step now. Ooh, yeah.
If we add an electron to the bottom, then are you like adding it like for the carbons to cancel out?
For the oxidation numbers on the carbons, because the oxidation number of oxygen didn't change from left to right, so we don't have to worry about that. The only oxidation number that changed was carbon. It went from a 3+ to a 4+, which means if you go from if you go to a more positive, you lost an electron somewhere. So we have to put that in the equation. No, because the oxidation number didn't change. It's -2 on the left, it's -2 on the right, so we don't have to worry about it. The only time you have to do this is if your oxidation number changes. Okay, so the next step says that we need to multiply the reactions by a whole number so that our electrons will cancel out. Right now we have 5 electrons in the top one, we have 1 in the bottom one. They're on opposite sides. There's one check to make sure that we're doing everything correctly, but we want them to cancel out. So what's the lowest common multiple between 5 and 1? 5. So I am going to get a different color so that you can see this. I am going to multiply this whole reaction by 5 so that I can get my electrons to cancel out. So if I multiply this entire thing by 5, it's going to change this coefficient to 5. It's going to change this coefficient, the 2, right? The 2 in front of carbon dioxide. It's going to change that to, 10. I had 5 in my mind. To 10. And it's going to change my electrons to 5. So remember in algebra how what you do to one side you have to do to the other side? Same concept here. We can't just multiply the electrons by 5. We have to multiply the entire thing by 5 in order for it to work. So now, are electrons going to cancel out? Yes, so now we can move on to the next step. We need to put the 2 half reactions back together and we can cancel out like terms. So, let's get another color. Let's do yellow. Okay, is anything going to cancel out? Yes, my 5 electrons are going to cancel out. Okay, let's see. Anything else? My hydrogens, nothing's going to cancel out my hydrogens. Nothing's going to cancel out. Nothing else is going to cancel out, right? We don't have anything else to cancel out, correct? So then you can just rewrite it. So we're going to have 8 hydrogens plus manganese oxide plus chromate. It's going to give you manganese plus 4 H2Os plus 10 CO2. Oh yeah, did I forget the coefficient? Sorry. The pink was hiding from me. Did I forget one anywhere else? Yes. And at this step, it should be a balanced redox reaction. Lots of steps, right? None of it's really hard. Lots of steps to try to remember how to do. Okay, let's do another one. We're going to do another acidic one before I throw in a basic one. Are you guys ready? Can I erase this now? Yeah? Okay, so let's try this one out. Sorry, I got distracted. Okay, so an acidic solution of potassium dichromate is added to a solution of iron nitrate. Uh-oh, I just made this a lot harder, didn't I? Why did I just make this a lot harder? We have to actually write it out. I didn't give it to you. So we can do this. Potassium dichromate. Well, I'll be easy for you. Dichromate is, it is Cr2O7, and it has a -2 charge. So we need to add potassium to it. So how do I add potassium to it?
K2.
K2. And I'm going to go ahead and put parentheses around that just so that you guys remember that that is a polyatomic ion. We're going to add potassium chromate to iron nitrate. Iron has a +2 charge because of my Roman numerals, right? Nitrate has what kind of a charge? -1, so we know we need 2 of them. Okay, that's going to give us what kind of reaction, first of all?
Double replacement. Wait, maybe the 2 after.
Did I forget my 2? Okay. I'm going to make this a lot harder. Yes, this is going to be a double replacement reaction, but we also have to remember our solubility rules, right? We also have to remember our net ionics. So right off the bat, nitrate potassium. What do we know about nitrate potassium?
Always soluble.
Always, always, always soluble. So when we have a net ionic equation, what's going to happen to potassium and nitrate? They're going to be our spectator ions, so they are going to disappear, right? So instead of worrying about those right now, we're going to worry about our chromate and our iron. Okay? No, we're gonna worry about potassium and iron. They're not gonna like disappear completely. But okay, so this is what I mean. So we're gonna kind of forget about potassium and nitrate because they are spectators. So basically what we're gonna do, we're gonna break it into half reactions. So we're gonna start off with chromium or dichromate. Okay, dichromate is going to give us, if you look at your handy dandy cheat sheet, what is it going to do? This is an acidic solution. It's going to form Cr3+. Okay, our other half reaction is we're going to have iron, which I know that iron was 2+, correct? Okay, there is a rule for metals. Is everyone listening? Isn't iron a metal? It's metallic, right? Okay, metallic ions always go up in one charge. So it's going to start off as 2+, but then it's going to end up as 3+. That's what metals do in redox reactions. They always gain a positive or lose a negative, right? Because you can't gain a positive. So you lose, they'll always lose an electron. So they are always going to be our oxidizers because they are always going to lose electrons. Oil rig, oxidation is loss, correct? Okay, that's just the rule for metals. So if you guys want to write that on your cheat sheet, metals lose an electron, you can if you want to. Okay, so now we've gotten our half reactions. We're ignoring potassium and nitrate because they're spectator ions, so they're always going to cancel out on both sides, correct? So now we need to we need to figure out oxidation numbers. We need to balance. We need to add waters and hydrogens, right? So first of all, let's figure out our oxidation numbers. We know that chromium's product has an oxidation number of 3+, but we need to figure out what chromium is on the other side, right? So chromium, or 2 chromiums, I guess, actually, because there's 2 of them there. 2 Cr plus 7, 2 minuses, correct? Has to equal 2 minus. So 2 Cr minus 14 equals -2. So 2 Cr equals 12. So Cr has to equal. So on this side, we have chromium is a 6+, and I'm going to write that in so we don't forget, correct? Okay. Iron, do we have to do any oxidation numbers? No, because we were already given all that information, so that's a little bit easy for you, right? So now let's start the balancing process, now that I figured out oxidation numbers. So, okay, our chromiums aren't balanced, so we have to balance them first, correct? How do I balance chromium?
2 on product.
I need a coefficient of 2 on the product side. Now everything is balanced, so now we need to start balancing oxygen. How do I balance oxygen?
7 waters.
I need 7 waters on the right side. But that messed up my hydrogen, so now I need to add something to my left side.
14
I need to add 14 hydrogens. Everything looks nice and pretty and balanced to me. What about you guys? Yes, so now let's look at iron. Is iron balanced? Yep. Okay, so we have balanced everything. The last step in your balancing is you need to add charges. We need to add electrons to balance out our charges, right? So let's look back at chromium. Chromium started off 6 plus, ended up 3 plus. So we need to add how many electrons to which side?
3 electrons to the reactant.
We need to add 3 electrons to our reactant side. Iron started off 2 plus, ended up 3 plus, so we need to add
1 electron on the product side. We have to.
Would it always be opposite like that?
It should.
sorry, repeat again.
Will it always be opposite? You add electrons inside, you'll always add 2
Mhm.
electrons?
If you're doing it correctly and you have your because basically one should be doing oxidation, one should be doing reduction. So your electrons should be on opposite sides. If they're on the same side, you probably messed up somewhere. Probably messed up on finding your oxidation number, so on and so forth.
Do we have to add the electrons for just like you don't get it for like
Oxygen, the oxidation number on oxygen on the left in chromate is -2. On the right for water is -2, so it didn't change. You only have to add electrons on the oxidation numbers that are changing. And I don't think I would give you one where 2 oxidation numbers change. That would be really mean. I don't think I would do that. Okay, so now what do we do? Nope.
So make the electrons equal.
We have to make our electrons equal, correct? So to do that, we have 1 on the bottom, we have 3 on the top. So we need to multiply this entire thing by 3, correct? So it changes this coefficient to 3, changes this coefficient to 3, and it changes this coefficient to 3. Okay, now what do I do? Cross things out and write your final equation. So this 3 electrons cancels out this 3 electrons because they're on opposite sides, right? Does anything else cancel out? Nope. So then I write we're going to have 14 hydrogens plus dichromate plus 3 irons. Going to give you 2 chromiums plus 7 waters plus 3 irons, 3 plus. Yes. Not hard. Lots of steps. No. No. That was just as we wrote it so we wouldn't forget what it was. Okay. Yes. Yes. Okay, so this is how you do acidic solutions. We add water and hydrogens because we know acids donate hydrogens into a solution, right? What do bases do? They do hydroxide, so we have to do something different. So for basic solutions, basically we do the same thing. Doesn't this look exactly the same up through step 4? We write the half reactions, we balance everything except hydrogen and oxygen. We then balance oxygen by adding water. We then balance hydrogen by adding hydrogens, right? Hydrogen ions, which is exactly the same as what we're just doing, except we know that bases don't donate hydrogens. They donate hydroxides. So what we have to do is we have to then add hydroxides to both sides to cancel out the hydrogens.
So we're adding the hydrogen and canceling them back out.
Correct. So it's just basically adding one more step. Then we cancel out any extra water, any extra hydroxides. Remember how in the ones in the acidic solutions, really the only thing that canceled out was our electrons. This time we're probably going to have water on both sides. We're probably going to have hydroxides on both sides. We're probably going to have hydrogens on both sides. So we're going to have more than just electrons to cancel out, but it's really not that much more difficult. Yes. Still have electrons, but this time we'll definitely have water. Sometimes we'll have hydroxides. Sometimes we'll have hydrogen. So let's just do an example, right? So this time we have an alkaline solution. Alkaline, I'm not going to write this down, is a fancy word for basic solution. So when you see alkaline, I mean basic solution. Okay, a solution of potassium permangate is mixed with an alkaline solution of sodium sulfite. Ugh, I'm so mean. I didn't give them to you. So, what is permangate? MnO4. Ooh, we used that a minute ago, didn't we? And it has a 1 negative. Okay? So potassium permangate, so we're going to have K, correct? Is mixed with an alkaline solution of sodium sulfite. So, what's sulfite? Not sulfate. SO3, 2 negative, which means we need 2 sodiums, correct? We really don't have to write this reaction out because we can do this based with this information, right? Uh-oh, something, red flag. Solubility. Sodium and potassium are always soluble, so they're going to be spectators. So let's just, we're going to ignore those guys, and we're going to do this with the other pieces of information, right? Okay, so let's start writing out our half reactions and finding out oxidation number. So I'm going to start with manganese oxide, or permangate. What in the world does this do in a basic solution? It does not form manganese. It forms manganese dioxide, so MnO2. Is there a charge? Nope. Okay, so we also have sulfite, correct? Is that on our cheat sheet? Yeah, sulfite ions, what do they form? Isn't this a sulfite ion? SO4, so it's going to form sulfate on our cheat sheet, correct? Okay. You see sulfite ions down there? Close to the, about halfway down. Okay, learn to love our cheat sheet. I'll let you use it on your test. It's going to go in your resource packet that I've given you already, okay? Alright, so now we have our half reactions written out, correct? So now we need to start the balancing process. So first off, we need to balance everything but oxygen. So let's look at our first half reaction. Let's look at manganese. Is it balanced? Yep, what's not balanced? So how do we fix that? You add how many waters? 2 waters to the left side, which then messes up our hydrogens. 4 hydrogens, and we forgot our oxidation numbers. We'll do that in just a second. Okay, let's just go ahead and do the same thing to the bottom one. And then we'll do our oxidation numbers here in just a second. So, is sulfur balanced? What's not balanced? So, where do I add water to? To the left. And that means I have to add hydrogens to the right. How many hydrogens? 2. Okay, we forgot to find our oxidation numbers, and honestly, we already did manganese, or permangate in the first example, so it had an oxidation number of +3. So I just looked back at our first example, because we already had permangate, correct? Why do the math twice? Okay, this one over here, what's the charge of manganese on the right side? 4+, correct? Oxygen's -2. We have 2 of them, so that's -4. So that means manganese has to be +4. Correct. Okay, so let's look at sulfur. Let's do the same thing for sulfur. Sulfur, so S plus 3 times 2 negative has to equal 2 negative. So that means my S is going to equal 4 positive, right? Did I do my math right in my head? Sometimes I don't. Did I look at the wrong thing? I looked at chromium. I'm sorry. Tanya's correct. I was looking at chromium instead of manganese, so we got 7 plus. Okay, so sulfur, 4 plus. Did I do my math right? Anyone want to double check me? I think I did it right. Okay, then we have sulfate, so we need to do the same thing. So sulfur plus 4 oxygens has to equal 2 minus again. So this time sulfur is going to be 6 positive. Okay. So now I'm going to erase all of that work so that I have more room to write. Okay, so now if we look back at our steps, it said we need to balance everything except hydrogen and oxygen. Then we need to balance oxygen. Then we need to balance hydrogen. We already did that. But now we have to add that other step where it says add hydroxides to both sides to cancel out the hydrogens. So we're going to basically add hydroxide to the opposite side. So if we look at our manganese one, we have 4 hydrogens in our manganese half reaction, right? So to cancel that out, we need to add 4 hydroxides to this side to cancel out those hydrogens, correct? But what we do to one side, just in algebra, we do something to one side, we have to do it to the other side. So I also have to add 4 hydroxides to this side. But we know something about hydroxides and water, don't we? What do we know about hydroxides and hydrogen? These two things are going to combine to make water, right? Okay, so let's do the same thing to the bottom. We can't have hydrogens. This is a basic solution. So we have to do the opposite. We need to cancel out the hydrogens by adding hydroxides. How many are we going to add? 2. But what we do to one side, we have to do to the other side, right? So we have to add 2 hydroxides on this side, and we have to add 2 hydroxides on this side, correct? But we know something about hydrogen and hydroxide, right? These two things are actually going to form 2 H2O's, correct? Alrighty.
So the only way we can make sure it's not the same coefficient as long as it's both have the same coefficient.
Alright. We're getting there, right? Now we need to balance out our charges. So let's look at our oxidation numbers. Manganese started off 7 plus, it ended 4 plus. We can't lose electrons, so we need to add how many electrons to which side? Left. And I'm running out of room, so I'm really sorry if this gets hard to read. So we need to add 3 electrons on this side, correct? Okay, so now we need to look at the bottom one. We started off with 4 plus, we ended with 6 plus. We can't lose electrons, so we have to add 2 electrons over here. Uh-oh. Oh. Least common multiple is going to be 6. So we have to multiply both reactions by something, correct? So we're going to multiply the top one by 2. We're going to multiply the bottom one by 3. This is going to be fun, right? So we don't have 4 waters, we have 8 waters. We don't have 1 permangate, we have 2. We don't have 3 electrons, we have 6. Okay? So go ahead. I want you guys to go ahead and multiply those through as your homework. Come back with a balanced equation tomorrow. Okay?
That is a lot more complicated.
8.
It's just, like, I think it's kind of easier than I thought, but you just have to be able to do it. Yes.
I don't. Where's 14 coming from?
You don't have any hydrogen. You can't make any more water because you can't see hydrogen out.
But like I'm just wondering because okay, so I would just replace these and not worry about them and just
Yeah,
make
I would
them
just
for
make them water. Uh-huh.
Okay, I was just wondering because when I wrote it out, I forgot to do that, and
Yeah, I always put a square around them and then make it those two up.
You should keep that up for the chemistry people watching. You should leave that up as tactic. When you take a picture of that, be like, my life. Have the chemistry people walk in and be like, what?
What is going on?
Just go through all the notes and tell this little entity today. Be like, oh, you guys are ready for this? They're next. Sure. You know those days where like you give them a break and you let them work like
Retakes today. Let's take it.
Yep.
And that's the retake. There's your homework. That's it. There's your homework. That's only one problem. I feel better about this though.
Did you draw this?
They told me to go ask him if I could. So
Did you mess up a couple times?
I was like,
No, we're balancing.
"JV tonight?" He goes, "No."